So there's another very important principle that we need to consider when it comes to exploring the realm of the really tiny. So again, things like subatomic particles, the nucleus, etc. And that principle is known as the Heisenberg uncertainty principle. And when we first talk about this, it may seem, kind of difficult to grasp, to wrap your mind around because it doesn't quite make a whole lot of sense. But it doesn't make a whole lot of sense on the macroscopic scale. On a submicroscopic scale, though, it actually does make sense. So this applies to the realm of the really, really, really tiny. Okay, so on a subatomic scale, electrons, protons, neutrons, etc., the Heisenberg uncertainty principle says that it is impossible to know both, so simultaneously, meaning at the same time, both the momentum, P, and the position x of a particle with 100% certainty. Okay, and we can think of the momentum as being analogous to, it's not the same thing, but the momentum would be analogous to the speed. It's not the same, but it's very similar to that. So that principle, again, applies to subatomic particles. Specifically, now we're looking at the electrons. Okay, so what that means is the more you know about one thing, the more certain you are about, let's say, the position or the speed or the momentum, let's use the correct term, the less you know about the position. That's the other term. Okay, and then vice versa as well. So the more you know about the position, the less you know about the momentum. Okay, so you know more about one at the expense of the other. And that is encompassed in an equation. We have delta x. Okay, delta x is the uncertainty in the position. So where that particle is, and that's in meters. And then delta p corresponds to the uncertainty in the momentum. Okay, so we can factor out, because momentum is the mass times the velocity, we can factor out the mass in this term. We can simplify it a little bit now. So we have the mass times now the change in, so delta U here would be the uncertainty in the velocity. Okay, so we said before it was analogous to the speed, right? And this is why, because momentum is just a product of the mass and the velocity. So we multiply those two uncertainties together, being greater than or equal to h Planck's constant over 4 pi. So we can take a look at an actual example and put some numbers behind this. Okay, so it says an electron in a hydrogen atom is known to have a velocity of 5 times 10 to the 6 meters per second, plus or minus 1%. Okay, so 1%, that's important because that's the same as 0.01. Okay, so this is the speed or the velocity, and then that's the uncertainty. So the uncertainty, right, is going to be important here when we start doing this. We want to calculate the minimum uncertainty in the position of the electron, and then given the diameter is less than 1 angstrom. An angstrom, by the way, is 10 to the negative 10 meters. Comment on the magnitude compared to the size of the atom. Okay, so we have our equation that we can use, the uncertainty Heisenberg uncertainty principle equation. The mass of the electron, we can look that up, and we want to make sure that it is in kilograms. Okay, we need kilograms as our unit because we saw Planck's constant here. It needs to be. So you want to double check this. This is a very, very common source of error. And then H needs to be in the right unit as well. Kilogram meter squared per second. We want to make sure that we have those units. All right, so what are we looking for? We're looking for the uncertainty in the position of the electron. And the position there is delta x. Okay, so we're trying to find this thing. We can substitute everything else into that equation. So our uncertainty in the speed, right, is 1% of the velocity 5 times 10 to the 6. Okay, so you multiply the 1%. That's 1% of u. Okay, so that's 5 times 10 to the 4 meters per second. And then delta x would be equal to, we rearrange our equation, so h over 4 pi times m times delta u. So we have our h, substitute that in, 4 pi, substitute that in there as well, times the mass of the electron, times the change in the uncertainty. So if we substitute that in, what we find that then it's greater than 1 times 10 to the negative 9 meters. Okay, so that's my uncertainty in the position is what I get. And again, you can confirm this. It may seem simple enough plugging into your equation, into your calculator, but make sure that you do that. And 1 times 10 to the negative 9, okay, this is my uncertainty in the position. And then up above, we said that the diameter of the hydrogen atom is less than 1 angstrom. Okay, so an angstrom is 1 times 10 to the negative 10 meters. That's the diameter of the atom. So when we compare these, we find that the uncertainty in the position is actually 10 times the size, the diameter of the atom. And you think about that, right? Uncertainty being 10 times larger than the atom, right? It does make sense if the uncertainty in one factor here is small, right? So 1% uncertainty in the velocity, well, then the uncertainty in the position is going to be fairly large as well. Okay. So when you do calculations like these, just double check that you're inputting the correct units. Double check that you're actually doing the uncertainty rather than the speed, for example, or the velocity, but you're doing the uncertainty. And keep track of your units as you go through. They will help you figure out the fact that you've actually done it correctly. So considering that fact that we're unable to simultaneously know with certainty what for the electrons, for example, its position and its speed, we then have to now take a deeper dive into how we actually express or view the electrons in any atom. And without going into a whole lot of detail into quantum mechanics and physics, etc., we'll just sort of gloss over the surface of this. When we start looking at the quantum mechanical description of the simplest atom, which is the hydrogen atom, Erwin Schrodinger came up with, derived a whole host of equations to help us describe the hydrogen atom, and specifically now in terms of the electron. So he came up with a bunch of complex math. And again, beyond the scope of our class, if you go into physics and go into physical chemistry, for example, you'll talk a lot about his equations. So his formulas incorporate both the wave particles and, I'm sorry, the wave characteristics and the particle characteristics of those electrons. So the wave behavior is described by a function called a wave function, which has this symbol, kind of looks like a trident. This is the Greek symbol psi, right? It kind of sounds like phi that we talked about before, which is a different thing, the work function, for example, of the ejected electron in the photoelectric effect. It's not the same, right? They're not equal to each other, even though the names kind of sound similar. So when it comes to locating an electron in an atom, because the electrons are so small, we deal with the quantum world and we deal with the uncertainty principle. The best we can do is to talk about the probability of finding an electron in a certain area or a certain volume of space in a particular atom. And that probability is proportional to the wave function squared, psi squared, and we call that the electron density. Okay, so psi squared is electron density, and that gives us the probability. Okay, what are the chances of finding an electron in a particular area? So we cannot say with 100% certainty. Instead, what we define is the most likely region an electron to be at any given time. Okay, and again, that may not sit well with you, but when it comes to the quantum scale and the really, really tiny scale, that's the best that we can do. We deal in probabilities. Okay, what are the chances of finding an electron in one location versus another? So for example, if this is my nucleus over here, right, I may have a 99% chance of finding an electron in the region that I just highlighted in blue, right? So somewhere in this region, okay, maybe there's a 99% chance of finding an electron. Now, it's not that you can't find the electron out here. Okay, it may be out there, but it's very unlikely, very, very unlikely to be outside of that region. And that's what we deal with when it comes to quantum mechanics and the quantum mechanical treatment of atoms and of electrons and of molecules as well.